Okay, so on your packet, go ahead and turn to page 8 if you have not yet. This should be the first blank page. So what we're going to do is kind of like some more mean value theorem. And this is just, this problem specifically is really good review for the quiz tomorrow. Okay, so first of all, in example 6, you are given a function. If you can figure out some things about this function without doing a lot of work, then that's great for you. Like later on, I see mean value theorem. What shape does this even make? A parabola? That's upside down, right? That's a real sketch there. Okay, we'll get to a specific graph at the end of this problem. But that thing's continuous. That thing's differentiable. So that's how you can easily kind of check those things off. All right, polynomials, quadratics in particular, they work out very nicely. That's why we use them a whole bunch. So in part A, it says find the equation of the secant line joining the points. Now, I just want to say something. If I took out this word secant, I could give this to an Algebra 1 class, and they could do it. So I know y'all can do it. When you don't let the word secant throw you off and make you think it's much more difficult than it is. I'm just asking you for an equation of a line joining these 2 points. Okay, so remember, for a line, you need a point. Well, we have 2 of them, so we get to just choose one. Doesn't really matter which one you choose. I'll just choose -2, 4. It does not matter which one. And then we also need a slope. And here we're going to need both of these. So how do you find slope of with 2 points? Change in y over change in x. So the way you'd see this written most likely would be 0 minus 4. And if I start with the 0, then on the bottom I have to start with the 2. 2 minus -2. You could go in reverse order as long as you stay consistent. So that's -4 over 4, which is -1. By the way, that's the average rate of change. I'm just writing it now because it's going to help us later. So that's great, but I haven't written the answer yet, which is find the equation of the secant line. So this is where you have to use, point slope. Y minus, now since I chose this point, I need to do y minus 4 equals the slope, x minus -2, so I'm going to make that +2. And that's it. That's your answer. There is an alternative version of this answer. First of all, we could definitely simplify if we wanted to. We don't need to. But what if I had chosen chosen, that's not really good English. What if I chose 2, 0? Then my answer would be y minus 0 equals -1, x minus 2. Okay, so you could choose either point. And if we simplified both of these, they would actually look identical. Okay. So then part B starts with the mean value theorem. If I'm going to use mean value theorem, I need to state that f is continuous and differentiable on the interval -2 to 2. And I get that I'm changing these to brackets. Truly, f is continuous and differentiable everywhere. I just went ahead and made it a closed interval so that it would fit the mean value theorem. And they kind of even give you a hint as to what mean value theorem says. It says tangent line is parallel to secant line. Well, I already found the average rate of change. That's -1. Okay, what I need to do now is find the instantaneous rate of change. This is where we get to use calculus. So what next? Take the derivative. If you're ever stuck and you haven't taken the derivative, that's not a bad move, because it happens in most problems. So if I look up here at the function f of x, I have -2x minus 1. So mean value theorem. There's lots of different ways to say it, but it's what we want to do. It's where these two things equal each other. The derivative equals the average rate of change, the slope of the secant line. So you always want to set up an equation, and then you're solving for x. So go ahead and solve for x in this equation, and that's your answer to this part. What'd you guys get for x? 0. Now, it's probably best if we go ahead and say c equals 0 because they used c. If you left it as x equals 0, you're not losing points on that. That's okay. All the meaning and intent is still there. Okay, so for part C, it's now we're finding another equation of a line, so I need a point and a slope again. But now it's through C. So if C equals 0, x equals 0, my point has to be 0, comma, and then I got to figure out what the y value is. They don't tell me, so where do I go? Go back up to the original function. If x is 0, what's y? 6. You just plug 0 back into the original function. That's how you're always going to find y given x, the original f of x. Okay, what about slope? It's the exact same. You can think of this two ways. If I really did correctly use mean value theorem, I should be able to plug my 0 into the derivative and I get -1. But even better than that, it has to be the same as the slope. You know, the slopes of these two lines need to be the same. So then we just write out the equation of the line. And of course that can be simplified, and you can do that or you don't have to. Before we move on, can anybody tell me what the relationship is between those two lines? They are parallel. How do you know that? It told us to do that, right? And that's part of what mean value theorem is. Okay, now Friday when we did this, we actually started with a graph and we let the graph help us through the problem. We were able to do this without a graph at all. And what we're going to do on part D is we're actually not going to use a graphing utility. We are going to just graph this by hand just for practice, but we're going to use it to confirm our results. Okay, so we already know several points of our parabola. Okay, 0, 6 is one of them. What else? What other points did they tell us this parabola hit? -2, 4, and 2, 0. And if I just kind of put these together to make a parabola, that would be pretty good. But if I wanted to make it more accurate, I need to like plug in 1. I need to plug in -1. Okay, so take a moment and go ahead and do that. And remember, you're plugging it into the original function, which was -x², I already forgot, minus x plus 6. So you're just say maybe taking 1 and you're plugging 1 in for x and figuring out what is the y value. And the more points you plot, the more accurate your parabola will look. Okay, so that's my f of x. Let's label it somewhere on there, f of x. And now let's graph the secant line. Okay, you don't actually have to start from scratch and try to get that into y equals. Just do what we did to find the line. Let's connect. Let's connect negative 2, 4 to 2, 0. And that's our tangent line. And you can confirm here that the slope is negative 1. So with the graph, that part's even easier. Oh, yeah, sorry. If you're listening to this, make note of this. I'm just being weird. That is the secant line. Thank you, Mia. We just found out in part C that the tangent line goes through the point 0, 6, also has a slope of negative 1, so try to make sure that your line has that same slope. And it's really obvious now that these two lines are parallel. Okay, now if you can follow through this problem, you're in pretty good shape for the quiz tomorrow on the mean value theorem part. Okay, any questions? We have one more example to do today. Okay, let's turn the page. Let's look at example 7. It's kind of a weird one, but I want you to notice a couple things that should kind of like draw your attention. This is a continuous differentiable closed interval graph. So what does that mean for our theorems, Anthony? Can we use our theorems if we have a continuous differentiable closed interval? Yeah, so continuous, that was good enough for intermediate value theorem. Continuous on a closed interval, that was good for extreme value theorem. And you put in differentiable, that's mean value theorem. So we may use any of those three theorems. This may or may not be a mean value theorem problem. It actually brings in more than one aspect. Okay, now, obviously they don't have the whole graph, right? There's a big chunk missing. Okay, it starts right here and ends right here. And what I want you guys to do is fill it in however you want. However, what can you not have in your graph? A cusp or a hole or a vertical asymptote. It has to be a smooth curve. It can be boring. I don't want to say boring. Standard, classic, whatever. All right, or you can make it go up and down and all that, but your graph just cannot have a cusp. And I'm not going to graph mine on here because I want to make sure that you're looking at your graph and we're all going to be able to answer the question. And it's good for us to have different ones. So once you get yours, I want you to peek over at your neighbors. See if they drew what you drew or something different. If you see a neighbor's paper with a cusp, kindly and politely point it out to them. Okay, so here we're going to answer these questions first experimentally. A, explain why f must have at least one 0. And here 0 is just that good old x-intercept. So I want you to raise your hand if your graph has at least one x-intercept. Okay, does anybody's not? Do you think someone could draw the graph to where they do not cross the x-axis? No. Right, then the graph has to be continuous. However they drew it, it has to cross through. Okay? And this is what I know a lot of people draw. Some of you got creative and you went like that or something like that. But has to go through it. Has to cross the x-axis. Okay, so that makes sense, but now we have to explain it. So let's think about the three theorems we have: IVT, EVT, and MVT. And I want you to think of it this way. At the two endpoints, the y value is 1 and -4. What number has to come between 1 and -4? 0. Which theorem does that sound like? I said in between, intermediate. Okay? So what we're going to do is we're going to say, okay, first of all, we're going to write out the inequality. And by the way, let's just put a big f is continuous and differentiable. This will just apply to anything we do after this. On the closed interval, -10 to 4. This will apply to everything. So if 0, the y value of 0, has to be between those two, let's relate it back to our function. What was -4? It was f of 4. What was 1? It was f of -10. So, and that's really all the work you have to show for IVT. So we can say, therefore, by intermediate value theorem, and then I'm just going to use the same language. F must have a 0 on, or you can always say on or in. Okay, so we haven't done an IVT problem in a long time. But I don't want to do that. I don't want to do it where for 2 months we haven't done one. So it'll kind of creep up on us from time to time. That's good. It's good to review. Okay, so we've done IVT. The next one has to do with either EVT, extreme value theorem, or mean value theorem. Okay, let's first experimentally see if this even works with everybody's graph in here. Explain why f prime must also have at least one 0. So they're saying, explain why f prime has to equal 0. And what are these zeros called? So look on your graph. Okay, what I want you to do is to make a big point everywhere f prime equals 0. So think about how are we going to figure that out? F prime represents slope. So where is the slope of your graph equal to 0? Where does the graph flatten out for just a moment before it changes direction? And so what are these zeros called? Relative max and mins. Okay, so let's go ahead and put that over here. And I'm just going to use relative extrema for the general answer. Okay, did everybody have at least one? Was there anybody that didn't have any? If I had had a cusp, do you guys see how it could be where there wasn't one with a cusp? That's not differentiable. So that's why that piece was important. Okay, so, and I could see us kind of going either direction here, but anybody have an inkling whether this sounds more like extreme value theorem or mean value theorem? Yeah. Okay, so I want to show something to you. Extreme value theorem is what we're going to use. Mean value theorem would definitely work here if instead of this point, don't write this on your paper, just watch what I'm doing. If that point had not been down there, but had maybe been up here. Okay? What is the average rate of change between these 2 points? What is? It'd be 0, right? The slope from start to end would be 0. And so if the average rate of change was 0, then what else would we know? The instantaneous rate of change would be 0. And so that would actually be an easier problem if one of these points, if they had repeated. Basically, if any of the points right here had repeated height, if they had had the same y value. Okay, so that would be where MVT would definitely have helped us. Now, it's not like that, but I wanted to point it out. So what we got to do instead is we're going to use EVT. And you may not really know why or where it's going, but let's just think. We can use EVT, and what does EVT say? Like if I said by EVT, F has, well, like what does that tell us? Has an absolute max and min. Okay, now I'm going to stick, and I'm going to be more specific here because I don't really care about the max and the min. And let me kind of erase this to start back over. Is it possible that this point down here could be my absolute min? Yes, it could be, or my graph could go down lower, okay? Any of those things could happen. But is this point over here, in any way, could it be the absolute max? Not at all. So what does that tell me about my absolute max? It's not at an endpoint. It's somewhere in there, okay? So let's just get that down, and then let's decide like how that'll help us, okay? So by EVT, F has an absolute max. And by looking at the graph, we can see the absolute max does not occur at an endpoint. So if the absolute max does not occur at an endpoint, where must it occur? Somewhere in here at a relative max. So, and I will tell you, I've explained this different, I've written slightly different things for my third, fourth, and fifth, and every time I kind of change the way I say it slightly. What you got to make sure is, what you want to make sure you have here is that you're referring to EVT, you're talking about F having a max, and then you're relating it to the fact that, so F must, or you could say must, or you could just say F has a relative max. Because our absolute maxes and mins occur at endpoints, we cross that off here, or relative extremate. So if F has a relative max, what's the derivative at a relative max? 0, and F prime equals 0. So this was kind of a weird one. A was really more cut and dry. B was kind of strange. It was a different use of EVT. No. There's no proofs on the quiz. Other than just like what I've kind of already said, but nothing like this. So C says make a possible sketch of the function with 1, 0. So I want you to kind of look at your picture. If you drew something like this, then you already did that. Okay, if yours was wackier, go ahead and draw like a real basic one. Now, if you did something where it went up and down and up, how many zeros, how many, I don't want to say, I shouldn't say the word 0. How many places does F prime equal 0 on mine? 3. Okay, 3. So that thing down here says, okay, well, make it to where there's 2. So I'm going to erase mine. You do whatever you want. These are your notes at the end of the day anyway. So to get 2, what we need is, okay, that's good. That's 1. What I need is from here to here to level off, but not like loop-de-loo change directions. Okay, do y'all remember we talked a little bit about this last week? These types of things where the slope is 0, but it doesn't change direction. Okay, saddle point, if you want to know the name. Okay, so then E says, were the conditions of continuity of F and F prime necessary to do parts A through D? What do you guys think? Yes for both? Yep, continuity for sure. And we already said if F had had a cusp, then we would have been, we couldn't have done the problem. So yes. Before we